Hello, everybody. My name is Kirill Horoshenkov, and I'm professor of acoustics at the University of Sheffield. And also leader for the Pipebots grant, which aims to transform maintenance and detection of conditions in buried sewer and clean water pipes. Today, I'm going to focus on clean water pipes. It's a big challenge, and the reason actually why it's a big challenge because of the sheer length of this pipe network in the UK. You can see that it's over 300,000 kilometers of clean water pipes. And these pipes are not in very good nick. They actually leak a lot. So they leak over 1 billion cubic meters per year of drinking water in the UK alone. And because they leak water, they need to be dug out and replaced and tested. So as a result, there is 1.5 million roadworks per year associated with the rehabilitation of buried pipe infrastructure in the UK. And as a result, there is a big economic adverse impact on the economy, over £5 billion a year. And one big reason why it's happening is because the majority of leak detection management is reactive. So basically, it requires human intervention. It's slow and requires road closure and so on. And why is that? It's because all the existing inspection methods, they require somebody to come, set something on the pipe, and measure it and remove it, or analyze it by a human. So I'll just give you a brief outline what's happening in the state of art of the technology for leak detection. So they use ultrasonic guided waves where you have to apply this color on the outside of the pipe to send ultrasonic waves which reflect from a leak or from a crack or port joint in the pipe, come back and they human analyze the result. Or what they do is, well, they install hydrophones or accelerometers on the hydrants of the clean water network, and then they run analysis of the signals obtained from adjacent hydrants and detect noise from the leaking water inside the pipe. More advanced methods include smart ball, which is good technology, and basically it requires a human to drop the smart ball through a hydrant, and it's taken by the flow, following direction of the flow, recording its location, temperature in the pipe, and acoustical signature in the pipe. And at some certain point, a human being has to extract this ball from the pipe. It's good technology, but it again requires human interaction and somebody to analyze the data offline. Another technology which is also reasonably advanced, it's called Sahara, when somebody have to drop a tethered sensor in the water pipe and control its position using the cable and measure noise radiated from leak. In summary of the inspection methods, all these methods require human intervention, and as a result, they all cause disruption at the surface. So we have to park a van on the road, block off part of the whole road, and carry out the experiments, measurements. And also, they're very difficult to administer in complex networks. We've got quite a lot of valves and connecting pipes and so on. They just become reasonably difficult to make sense of the data collected by these methods. So what we're going to do about it? So one way is just to make the inspection completely autonomous. That's what this Pipebot grant is about. Basically, it aims to revolutionize buried pipe infrastructure management with the development of micro robots which are much smaller than the pipe diameter. And these robots designed to work in underground pipe networks and dangerous sites autonomously and cooperatively. This animation shows the results of computer simulation we carried out on a real 30-kilometer long pipe network on a small town in Yorkshire. And basically, our simulation suggests that it is possible to inspect this kind of network on a monthly basis using no more than a dozen of robots. So basically, you can bring the data back to the surface autonomously. So every single month, checking for leaks or broken pipes and so on. How we're going to do it? So government gave us £7.2 million in a form of 5-year grant, which started in March 2019, and it is going to continue until February 2024. It involves 4 academic institutions. University of Sheffield leads on it. It also involves University of Birmingham, Bristol, and Leeds. It unites over 40 researchers working on different topics, which I show you on the next slide. And we're supported by over 30 industry partners. So what we will do, we broken up the program of work in 7 related research themes. And these themes relate to grand scientific challenges, such as accurate sensing, robust delivery platform, accurate navigation, effective data management, and system engineering. Basically, we develop a science for new sensing, which can be put on robots which can deliver the sensing platform, control algorithms, which make these robots to work autonomously and collaboratively, navigation algorithms, which can work in feature-deprived pipe environment, communication power techniques to make sure we allow robots to talk to each other and send the data back to the surface and be controlled from the surface, and also emerging science to make sure we connect to other grants, to make sure we don't miss any new developments which we can adopt for our technology. And also we've got a united theme which is to do with the system knowledge generation and user engagement, to make sure that we present data collected by robots in auctionable form and make sure we get buy-in from end users. Where we now, we are developing testing facilities. We've slightly been affected by COVID-19, but we resolve the situation now. Universities still remain open. So we make robots. We test these robots in these pipes. We write code to make sure these robots do what we want them to do. We also test navigation solutions on these robots in pipes. And also we develop theoretical and numerical models to understand better what the actual collected data really mean. The benefits of this approach, massive. So utility companies and their subcontractors will be able to autonomously monitor their system performance on an unprecedented scale, giving them early warnings to proactively rehabilitate buried pipes at a much reduced cost. Also, we give opportunity to instrument manufacturers to be able to produce new sensing and rehabilitation solutions and market it. And also, obviously, general public will definitely benefit if you got much fewer failures and interruption to the services, more sustainable water supply, and fewer road closure and less traffic disruption. What is going beyond Pipebots? Normally, university is pretty good in developing science and low TRL level demonstration of the science. Unfortunately, university don't go well beyond maybe technology readiness level of 4 or 5. Therefore, we are working on follow-on projects to make sure that we can find interested parties to take this technology beyond medium TRL level to high TRL level to ensure that water utilities will be able to adopt this technology because it will appear to be ready for them to work robustly in their systems. And also we're developing new governance framework to make sure these robots are safe and there is a economic case for putting them in the pipe networks. This program grant is not inner circle. We're open to collaboration with external academic and non-academic parties. So if you want to know more about this grant, do visit the website, which appears on my first slide. Or you can write to me directly via this email or to my colleague Ash Cooling, who is a program grant manager. And this is your email address. Thank you very much for your listening and stay well. Bye-bye.